Section 1 Introduction. We're going to talk about a new development in the field of large language models, LLMs. These models, which are trained to predict the next word in a sequence, have become incredibly accurate and fluent, leading to a variety of practical applications that were unimaginable just 10 years ago. Recently, researchers have been exploring large multimodal models, LMMs, which go beyond LLMs. One such model, Flamingo, combines a powerful language model with a pre-trained vision encoder, adding layers that can learn to understand the relationship between different types of data. This has proven to be very effective, especially in the context of zero-shot learning, where the model is asked to make predictions about data it has never seen before. However, most of these LMMs are trained on pairs of images and text, or on documents, and they don't take into account video data, which is another rich source of multimodal data. Moreover, the training objective for these models is usually to predict the next text token, and the vision part of the model is often not supervised, which limits the model's potential. In this paper, we present EMU, a new LMM that learns from both video and image data, as well as text. The goal is to predict the next visual or text token in a sequence, in an autoregressive manner, meaning that the model uses its own previous predictions as input for future predictions. Documents that include images, like textbooks or web pages, are a great way to represent complex concepts, and they have been shown to be very effective in teaching models to learn in a multimodal context. Videos, which often include image frames and subtitles, are a largely untapped source of multimodal data. They contain a lot of visual information and often have a stronger correlation with text than other types of multimedia documents. To make the most of this rich source of data, we convert different types of multimodal data, like videos with subtitles or web pages with images and text, into a unified format of interleaved image embeddings and text tokens. We first encode the visual data into embeddings using a visual representation model, EVA. These visual embeddings, along with the text tokens, make up the input sequence for EMU. Unlike existing LMMs, which only calculate the loss on text tokens, EMU takes into account both text tokens and image embeddings when calculating the loss. We use cross-entropy classification loss for the text tokens and a type of regression loss, called L_2 loss, for the image embeddings. EMU doesn't try to generate images in the original pixel space, because images don't have the same left-to-right causal dependency as language. Instead, we transform the visual embeddings into a causal latent space using a causal transformer. This takes the image encodings generated by EVA as input and outputs tokens that capture the causal dependency of the image. Once EMU has been trained with this unified objective and diverse data, it can be used for both image-to-text and text-to-image tasks. It can take multimodal prompts, like text, images, video, or a combination of these, and generate a multimodal response. For image generation, the visual embeddings are decoded by a fine-tuned diffusion model. EMU has shown impressive abilities, such as generating text and images in context, blending images, understanding videos, and grounding knowledge in the real world. We have tested EMU on a wide range of tasks, including image captioning, visual question answering, video question answering, and text-to-image generation. We have also created a multimodal assistant that can follow human instructions and interact with users through multimodal responses. Section Summary. In this section, the authors introduce EMU, a large multimodal model that learns from both video and image data interleaved with text. EMU is trained to predict the next visual or text token in an autoregressive fashion, using a unified objective that considers both discrete text tokens and continuous image embeddings. The model demonstrates impressive abilities in context text and image generation, image blending, video understanding, and real-world knowledge grounding. It is evaluated on various tasks such as image captioning, visual question answering, video question answering, and text-to-image generation. Section 2 EMU. Predict the next in Multimodality. We're going to discuss a system called EMU, which is designed to predict outcomes in a multimodal environment. This means it can process and generate outputs from a variety of different types of input, such as images, text, and video. EMU is made up of four main components: a visual encoder, a causal transformer, a multimodal modeling system, and a visual decoder. We use pre-existing models, namely EVA, Llama, and Stable Diffusion, to initialize these components. Here's how it works. When we feed EMU a sequence that includes images, text, and video, it first uses the visual encoder to convert the image into a set of dense visual features. These features are then transformed into a fixed number of visual causal embeddings by the causal transformer. The same process is applied to videos, with each frame being encoded into a set of visual causal embeddings. We use special tokens to mark the start and end of each image or frame. These visual causal embeddings are then combined with text tokens to create multimodal sequences, which are processed by the multimodal modeling system. In the final step, the visual decoder is fine-tuned to convert the visual embeddings back into a realistic image. One of the unique features of EMU is the causal transformer. Traditional methods of modeling images in a sequential order haven't been very successful, likely because images are naturally two-dimensional and aren't processed in the same way as sequential signals like text. To address this, we've designed the causal transformer to convert 2D visual signals into 1D causal sequences in a latent space. The causal transformer takes an image and its encodings as input and outputs a set of embeddings that capture the causal dependency of the image. The architecture of the causal transformer is similar to the decoder of a transformer, with each block consisting of a causal self-attention layer, a cross-attention layer, and a feed-forward layer. Unlike the Q-former, which captures bidirectional relations of input tokens, we use a causal self-attention layer to capture the causal dependency among the input latent embeddings. The cross-attention layer aggregates visual information from the image embeddings, treating the visual embeddings as keys and values, and the outputs from the previous causal attention layer as queries. Finally, we have the visual decoder. This uses a latent diffusion model to decode visual embeddings back into images. We initialize it with the weights of stable diffusion and feed it the visual embeddings generated by EMU. We've also made some modifications to the cross-attention modules in stable diffusion to accommodate the dimensions of EMU in stable diffusion. Section summary. The EMU model is a large-scale multimodal model that can perceive and generate outputs in different modalities. It consists of 4 parts: visual encoder, causal transformer, multimodal modeling, and visual decoder. The causal transformer module is used to transform 2D spatial visual signals into 1D causal sequences, while the visual decoder decodes visual embeddings into realistic images using a latent diffusion model. Section 2.2 Training Objective. We're working with a large and labeled dataset, which we'll call D. This dataset is made up of different types of sequences, which we'll refer to as X. These sequences could be a variety of things, like pairs of images and text, documents that alternate between images and text, or even videos with subtitles. Each part of these sequences, which we'll call X_I, could be a piece of text or an image. First, we transform all the 2D signals, like images and video frames, into 1D sequences using a tool called a causal transformer. We then put these sequences back into their original places in X. The result is a new sequence, which we'll call U. Each part of U, or U_I, could be a piece of text or a visual representation that's related to the visuals around it. We then try to match the likelihood of the original dataset, P, X, with the likelihood of our new sequence, P, U. We do this by maximizing the likelihood in a unified way, which can be described as follows. We aim to maximize the sum of the log probabilities of each U_I, given all the previous U's, and we approximate this to P, X. To achieve this, we use 2 types of losses. For the text parts, we use cross-entropy loss to guide the classification within a predefined vocabulary. For the visual parts, we use a type of regression loss called L_2. Our method of modeling different types of data gives our system, which we call EMU, the ability to handle many types of tasks involving different types of data. For example, if we give EMU 2 pairs of images and text that are related to the same task, it can figure out and complete the task with a new input. If the expected output is text, EMU will generate text. If the expected output is an image, we add an IMG token at the end of the input, and EMU will generate visual representations that can be decoded into a real-world image. Section summary. The training objective of EMU involves converting multimodal sequences into causal latent embedding sequences and maximizing the likelihood of the web-scale corpora in an autoregressive manner. 2 types of losses, cross-entropy and L_2 regression, are used to optimize this objective for discrete text tokens and continuous visual embeddings, respectively. EMU's unified autoregressive modeling allows it to serve as a multimodal generalist, capable of completing various tasks in a multimodal sequence by generating text tokens or visual embeddings based on the desired output format. Section 3 EMU Training. We begin by training EMU, our model, using a vast amount of data from the web in various formats. This includes pairs of images and text, from LAION2B and Leon Coco, mixed image text data, MMC4, pairs of videos and text, WEBVID10M, and our own mixed video text data, YT Storyboard-1B. All this data is structured as multimodal sequences, which EMU uses to learn how to predict the next element in a sequence in a unified, step-by-step way. After this initial training, we fine-tune an image decoder to convert visual data into realistic images. Let's delve into the data we use. For image-text pairs, we use data from LAION2B and LAION-COCO. LAION2B offers images paired with somewhat imperfect alt texts from the web, while LAION-COCO is a subset of LAION2B that includes 600 million images captioned by Blip. For video-text pairs, we use the WEBVID10M dataset, which is a large collection of short videos with text descriptions. These videos come from various websites and have a strong connection between the text and video content. We use certain rules to remove unrelated metadata, like the resolution of the original video or camera settings. For mixed image and text data, we use the multimodal C4, MMC4, dataset, which is an expanded version of the text-only C4 dataset. MMC4 includes about 75 million documents that mix images and text, with a total of 400 million images and 38 billion tokens. From each document, we randomly select a subsequence of 1024 elements, including up to the first 5 images in the selected sequence. We also randomly select 5 images and their corresponding sentences to create a subsequence of 512 elements. For mixed video and text data, we use videos with subtitles, which offer a scalable source of mixed multimodal data. We've created the YT Storyboard 1B dataset, which includes 18 million videos and their corresponding subtitles from YouTube, using the video IDs provided by the YT Temporal 1B dataset. Instead of raw videos, we collect storyboard images, around 1.8 billion in total, which are sets of thumbnails provided by YouTube for quick video viewing. The combination of these thumbnails and subtitles creates a naturally mixed sequence of video and text, ordered by timestamps. An example of this can be seen in the figure. More details about the datasets used for pre-training can be found in the appendix. Section Summary. We pre-trained our EMU model using web-scale data from various modalities, including image-text pairs, interleaved images text data, and video-text pairs. The image-text pairs were obtained from LAION2B and LAION-COCO datasets, while the video-text pairs were sourced from the WEBVID10M dataset. We also utilized the multimodal C4 dataset for large-scale image-text interleaved data and introduced the YT Storyboard 1B dataset, which consists of storyboard images and subtitles from YouTube videos. After pre-training, we fine-tuned an image decoder to generate realistic images from visual embeddings. Section 3.2 Pre-training. We start by setting up EMU's visual encoder using the 1 billion parameter version of EVA02, and the multimodal modeling LLM using the 13 billion parameter version of Llama. Llama is a transformer model that only decodes, while EVA02 is a vision transformer with 40 layers. The causal transformer, which includes 12 blocks each with a causal self-attention layer, a cross-attention layer, and a feed-forward layer, is initialized randomly. EMU, with its total of 14 billion parameters, is trained from start to finish. For training, we use different batch sizes, 128 for image text pairs, 64 for interleaved image text data, and 16 for both video text pairs and interleaved video text data. We use the Atom W optimizer with a first beta value of 0.9, a second beta value of 0.98, and a weight decay of 0.05. The learning rate decreases following a cosine pattern, with a peak learning rate of 0.0001 for the causal transformer, 0.00003 for Llama, and 0.00005 for EVA02, and a linear warm-up over 2,000 steps. For each video, we randomly select 8 frames for pre-training, and all images or frames are resized to a resolution of 224 by 224. For image text pairs and interleaved data, we randomly place each image either before or after its corresponding sentence. The model is trained on 128 NVIDIA 80GA100 GPS for 10,000 steps with about 82 million samples, 150 billion tokens in total, and the pre-training takes roughly 2 days. After pre-training, we fine-tune the visual decoder using both LAION-COCO and LAION Aesthetics, a high-quality subset of LAION5B, image-text pair datasets for the text-to-image task. We start the diffusion model with Stable Diffusion version 1.5. During training, we keep the visual encoder, multimodal modeling LLM in EMU, and the VAE in the diffusion model constant, only updating the parameters of UNet. For each training sample, we add the IMG token to the end of the input text and feed it into the multimodal modeling LLM, which then generates N visual embeddings in an auto-regressive manner. These visual causal embeddings are used as the condition for image generation training in the image decoder. We follow the model setups of Stable Diffusion version 1.5. We use the Atom W optimizer with a first beta value of 0.9, a second beta value of 0.999, and a weight decay of 0.01. We train the diffusion model with 32 A140G GPUs for 15,000 iterations. The batch size is set to 50 per GPU, and the learning rate warms up to 0.0001 for the first 5,000 steps, then decreases to 0.00005 and 0.00001 at 10,000 and 14,000 steps respectively. To further enhance sample quality, we randomly drop image embeddings condition by 10% of the time during training to enable classifier-free guidance. More training details can be found in the appendix. Section Summary. In the pre-training phase, we initialize MU's visual encoder with EVA02 and multimodal modeling LLM with Llama. The causal transformer is randomly initialized and has 12 blocks. We use different batch sizes and optimizers for different data types, and the total number of parameters in EMU is 14B. In the visual decoding phase, we tune the visual decoder using Laon Coco and LAION aesthetics datasets. We freeze certain components and update only the parameters of UNet. The diffusion model is initialized with Stable Diffusion version 1.5, and we use Atom W Optimizer for training. The diffusion model is trained with 32 GPUs for 15K iterations, and we employ various learning rate schedules and techniques to improve sample quality. Section 4. Instruction Tuning. We've used a method called language instruction tuning to help our pre-existing language models, like EMU, better understand and respond to user commands, and to adapt to tasks they haven't encountered before. This process involves using a variety of publicly available datasets, such as Shared GPT and Alpaca for language instructions, LLAVA for image-text instructions, and VideoChat and VideoChat GPT for video instructions. More information about these datasets can be found in the appendix. During the instruction tuning process, we don't make any changes to the original parameters of EMU. Instead, we fine-tune a module known as a low-rank adaptation, or LoRA, module. The main goal here is to make sure the model can understand and follow natural language instructions, which don't usually have much to do with visual features. So, we only add LoRA modules to the self-attention layers of the multimodal modeling LLM, and we don't make any changes to the vision encoder. We use a batch size of 128 and train the model for 10,000 steps. The learning rate starts off slow, warming up to 0.00001 in the first 500 steps, and then gradually decreases to 0 following a cosine schedule. The whole instruction tuning phase takes about 16 hours using 16 A180G GPUs. All the data we use for instruction tuning follows this format. Less than system message greater than user, less than instruction greater than assistant, less than answer greater than. Here, user and assistant are special tokens that represent the words user and assistant. The less than system message greater than changes depending on the task at hand, and you can find more details about the system messages we use for different tasks in the appendix. The less than instruction greater than and less than answer greater than slots are filled with the actual instructions and responses, but only the less than answer greater than is considered when calculating loss. We've tested EMU on a wide variety of vision language tasks, including image captioning, MS Coco, image question answering, VQA-V2, OK-VQA, VizWiz, visual dialogue, VisDial, video question answering, MSR-VTTQA, MSVDQA, NextQA, and text-to-image generation, MS Coco. More details about these benchmarks can be found in the appendix. We've evaluated our models, both before and after instruction tuning, in zero-shot and few-shot settings. Section Summary. The authors applied multimodal instruction tuning on EMU, a pre-trained language model, to align it with human instructions through supervised fine-tuning using publicly available datasets. They used a low-rank adaptation module called LoRA to align the model with natural language instructions, focusing on the self-attention layers of the multimodal modeling LLM. The instruction tuning phase took around 16 hours with 16 A180G GPUs. EMU was evaluated on various vision language tasks, including image captioning, image question answering, visual dialogue, video question answering, and text-to-image generation, in both zero-shot and few-shot settings. Section 5.10 Shot Evaluation. In this section, we'll discuss the zero-shot evaluation of our model. This is a scenario where the model is tested on tasks and datasets that it hasn't seen during its training phase. We use task-specific prompts to guide the model on what to do, without making any adjustments to the model's parameters. We'll start with multimodal understanding. We've tested two versions of our model, EMU and EMU-I, which is a version of EMU that's been fine-tuned with instructions. We used a technique called the multimodal chain of thought, which involves 2 steps. First, the model is asked to create a descriptive caption for a visual content. Then, the model is given both the caption it created and a task-specific prompt to produce the final result. To make sure we're comparing apples to apples with another model called Flamingo, we also used Flamingo's prompting strategy. This involved using 2 text-only examples from the task as prompts. Results obtained this way are marked with an asterisk. These prompts didn't include any images, which is like a few-shot text prompt approach. For more details on the evaluation, you can check the appendix. When tested on the COCO captioning task, EMU performed exceptionally well, achieving a CIDR score of 112.4. This score is significantly higher than other language and multimodal models, LMMs. EMU also outperformed other LMMs like Cosmos 1 and Flamingo 9b in a variety of image and video question answering tasks. For instance, EMU achieved an accuracy of 34.4% on the complex VizWiz VQA dataset, compared to Cosmos 1's 29.2% and Flamingo 9b's 28.8%. EMU-I, the instruction-tuned version of EMU, showed notable improvements. Despite having only 14 billion parameters, EMU-I outperformed the much larger Flamingo 80b model in several tasks. For example, in the VQA v2 task, EMU-I scored 57.5% compared to Flamingo 80b's 56.3%. In the VizWiz task, EMU-I scored 38.1% compared to Flamingo 80b's 31.6%. And in the MSVDQA task, EMU-I scored 36.4% compared to Flamingo 80b's 35.6%. Next, we evaluated the model's ability to generate images from text in a zero-shot setting, using the validation set of MS COCO. We randomly selected 30,000 prompts from the validation set and calculated the zero-shot Frechet inception distance, FID. Both EMU and another model, SDV 1.5, were used for generation, with a PNDM scheduler for 50 steps and classifier-free guidance for better quality. We set the scaling factor to 5.0 for EMU and 3.0 for SDV 1.5, as these settings gave the best performance for both models. EMU performed better than a concurrent work called GIL, which also generates images with LLMs. However, our model didn't perform as well as SDV 1.5 in terms of FID. This could be because the condition space of our visual decoder, image embeddings, differs significantly from the condition space of the diffusion model used for initialization, text embeddings, and our model was trained for a relatively short 15,000 steps. We believe there's potential for improvement by fine-tuning with more steps, or using a different visual decoder instead of pre-trained diffusion models that condition on text embeddings. Section summary. In the zero-shot evaluation, the EMU model performs well on tasks and datasets it has never seen before, using task-specific prompts. Without additional parameter tuning, EMU outperforms other language and multimodal models in tasks such as COCO captioning and image-video question answering. The instruction-tuned EMU model, EMU-I, achieves notable improvements and outperforms larger-scale models like Flamingo 80b in various tasks. However, EMU's image generation ability is inferior to SDV 1.5 in terms of FID, possibly due to differences in condition spaces and shorter training steps. Section 5.2 Few-Shot Evaluation. In this section, we'll discuss the performance of our model, EMU, in a few-shot evaluation and a qualitative evaluation. In the few-shot evaluation, we test EMU's ability to learn from a small number of examples. We provide the model with specific prompts and a handful of examples from the training data. The specifics of this evaluation can be found in the appendix. We compared EMU's performance in image and video question answering tasks to other models under a few-shot evaluation setting, where we used a small number of examples, k equals 2, 4, 8. We used the retrieval in context example selection, RICES, method, which was also used in the Flamingo model. EMU, which was trained with interleaved data, outperformed both Flamingo 9b and Cosmos 1 in almost all scenarios. For instance, in a 4-shot setting, EMU achieved a VQA v2 accuracy of 58.4% and VizWiz 41.3%, which is 2.1% and 6.4% higher than Flamingo 9b, respectively. EMU also showed strong performance in video text tasks. For example, it scored 21.8% in a 4-shot setting on the MSRV-TTQA benchmark, which is higher than Flamingo's 18.2%. We also noticed that as the number of examples, k equals 0, 2, 4, 8, increased, EMU's performance improved. These results highlight EMU's exceptional ability to learn from context. In addition to these quantitative benchmarks, we also conducted a thorough qualitative evaluation of EMU. EMU showed impressive capabilities that can't be measured by standard benchmarks. These include understanding real-world knowledge, interpreting multiple images simultaneously, understanding detailed video content, acting as a multimodal assistant, engaging in multi-turn dialogues, blending images, and generating text-to-image in context. For instance, EMU can generate images related to the context. In the first two rows of a figure, the images generated by EMU share the oil painting style of the context, compared to the corresponding images generated without context. EMU can also follow context-related instructions, as shown in the fourth row of a figure. This new ability to generate images is due to EMU's in-context ability of multimodal modeling, which uses LLM as initialization. We also compared EMU with other top-performing multimodal assistants in terms of their ability to perform typical image captioning tasks and follow human instructions. In one figure, we tested a slightly difficult instruction. Only EMU was able to correctly list 8 books written by Agatha Christie and then recommend one. Section summary. In the few-shot evaluation, EMU demonstrates superior performance in image and video question answering tasks compared to Flamingo 9B and Cosmos 1, achieving higher accuracy under different scenarios. EMU also showcases impressive capabilities in real-world knowledge grounding, multi-image understanding, video understanding, multimodal assistance, multi-turn dialogue, image blending, and in-context text-to-image generation. It outperforms other state-of-the-art multimodal assistants in tasks such as image captioning and following human instructions. Section 6. Related work. In this section, we'll discuss related work in the field. Multimodal pretraining is a method that learns how different modes of data interact with each other on a large scale. The BAIT series is a good example of this, as it transforms visual data into discrete tokens that can be pre-trained in the same way as language data. The third iteration of BAIT has shown impressive results when fine-tuned with a unified-style masked signal modeling objective. Flamingo is another model that has made significant strides in this area. It combines powerful pre-trained vision and large language models while maintaining privacy. It's the first to show impressive multimodal zero-shot and few-shot behaviors. As large language models, LLMs, become more accessible and influential, recent studies have started to build multimodal models based on them. An example of this is the BLIP series, which connects pre-trained vision and language models with a Q-former to bridge the gap between the two modalities. These language multimodal models, LMMs, typically use the prediction of the next text token as their training objective and do not supervise the vision data. EMU, on the other hand, unifies the modeling of vision and language. It aims to predict the next visual or text token in an autoregressive manner and further explores videos as a new source of interleaved image-text data. This unified modeling approach provides a versatile interface for various multimodal tasks that produce either image or text outputs. Recently, there have been attempts to build powerful visual multimodal assistants based on LMMs using constructed conversation data. We have also fine-tuned EMU using publicly available datasets to create a multimodal assistant. This assistant aligns well with human instructions on both images and videos. Section summary. In the related work, previous approaches to multimodal pretraining include BAIT and Flamingo, which achieved exceptional performance by bridging vision and language models. Other approaches, such as BLIP series, connect frozen vision and language pre-trained models with a Q-former to bridge the modality gap. However, these models commonly use predicting the next text token as the training objective and provide no supervision for vision data. In contrast, EMU unifies the modeling of vision and language by predicting the next visual or text token, leading to a generalist interface for diverse multimodal tasks. Additionally, recent studies have attempted to build powerful visual multimodal assistants using EMU and publicly available datasets.